This presentation is about basically predicting the occurrence of earthquakes using what are called TEC or total electron content in the atmosphere. So this work will be presented by Ms. Jacqueline Rivera, BS Physics student of UP Baguio. And with us today are her thesis panel, thesis examiner, Professor Alipio Garcia, retired professor in UP Baguio, and Professor Aladin Hasmin, professor in UP Baguio, Department of Physical Sciences. So, whenever you're ready, Jackie.
Thank you, sir. Yes, so good morning, everyone. I'm Jacqueline Rivera, and today I will be presenting my thesis entitled Quantifying the Predictive Value of Pre-Seismic Total Electron Content Anomalies for Daily Earthquake Occurrence Forecasting in the Philippines using a PMO-centered GNSS framework. So this presentation is organized into 7 parts. First, I will be discussing the background and the motivation of this study. Then we will be defining TEC, or Total Electron Content. Next, I will also discuss about the data sources, the study framework, then the methodology, which we will be further exploring on how TEC anomalies are detected. And finally, our results followed by the conclusion and recommendation. So we know that earthquakes are a major concern in the Philippines because the country lies in a highly active tectonic region. Their impacts extend beyond ground shaking that can definitely threaten communities and even public safety. Yet, despite all of this, reliable earthquake prediction remains a major scientific challenge. So one recent example is just last year's magnitude 6.9 Cebu earthquake, which resulted in 79 deaths and injuries. This impact could have been reduced if only they were alerted prior to the event. And this leads to the next question. Do we have any available earthquake early warning system as of today?
Earthquake that has already begun? How does shakeout work? When an earthquake occurs, seismic waves carry energy in all directions away from the epicenter. P waves, similar to sound waves, move quickly through the ground, followed by the slower and generally more damaging S waves and surface waves. Sensors detect the seismic waves and send that information to the machine processing center, which requires that at least 4 sensors detect the earthquake. If the earthquake fits the right profile, the USGS issues a shake alert message. Distribution partners then produce and deliver an alert to people.
Okay, so it is important to clarify that we don't have a shake alert like earthquake early warning in the Philippines. But even in the United States, this still gives them seconds to prepare, which is not enough. Given these velocities for P wave and S wave, we can estimate the lead time as shown. And as you would notice, those communities that are near the epicenter receives a little to no warning despite the fact that they are experiencing the strongest impacts. And this limitation motivates the question of this study as to why a longer lead time is crucial, because seconds may help people react, but these could help communities prepare. And this is the exact reason why we are investigating TEC anomalies as a possible source of information for pre-earthquake prediction. So before we define how TEC can be used in this study, it's best if we first define what TEC is. So it starts with a region in the Earth's atmosphere, which is the ionosphere. So ionosphere is found mainly on the thermosphere, and this is exposed to solar radiation. Because of that, it's filled with charged particles. It's measured, the number of electrons are measured in TEC, or total electron content. And it's also important to note that TEC varies with solar activities, geomagnetic storms, or space weather conditions. So we are probably wondering why or how can the process that starts underneath the ground possibly be connected to the changes observed above. So to explain why TEC may be investigated in relation to earthquakes, this study is motivated by these three proposed ideas: positive hole theory, electric coupling model, and the LAIC framework. So first, it is suggested that some crustal rocks, specifically igneous and high-graded metamorphic rocks, contains peroxybonds. So these peroxybonds are single oxygen-to-oxygen bonds, wherein when a tectonic stress builds up, this bonds breaks easily. And once it breaks, it displaces electrons on the rocks, and that electrons leaves an electron deficient site, which acts as a positive hole. And because of that, the neighboring electron tends to move in that positive hole, and then the vacancy it leaves will then again repeat the process until the entire ground is forms a charge movement, which makes the air near the ground ionize. So additionally, it is also reported that certain radon and thoron radioactive gases increase hours to days before earthquakes. And this radioactive gases naturally decays. Once it decays, it emits an alpha particle, which is high energy particles. And once it interacts with molecules, for example, with nitrogen and oxygen, it tends to knock off the electrons by Coulomb interaction, and that makes the air more conductive, which may modify the local vertical electric field above the stress region. So because the ionospheric region already has a normal or plasma drift, which is governed by the electrical field and the Earth's magnetic field, or the E cross B drift. Whenever there's a change, again, in the electric field, it is felt in the ionosphere. And once that happens, it might change the drift speed or the direction of the movement of these electrons, which, to put it simply, we may consider it as redistribution. So to visualize what LAIC framework looks like, so disturbance starts from the ground, and then together with the radion and thoron decay, it modifies the electric field, and then these electrons are now redistributed. So the idea is that electrons do not physically travel from the ground to the atmosphere. The idea is that whenever there's a redistribution, if the electrons move near this single GNSS path, it may appear as an increase in TEC. But if they are redistributed in a way that it moves away from this single GNSS path, then it will appear like a decrease in TEC. And this fluctuation is the exact TEC anomaly that is described in this study, wherein these anomalies are already reported globally, but it does not mean that it's universal or it's accepted everywhere. That's the reason why there's still a need of local validation in the Philippines. And this is the exact question that we're trying to answer, if the same anomaly patterns can be observed in the Philippine settings. So aside from the Philippines, complex tectonic setting, highly dynamic low latitude ionosphere, we only have a few single case studies. So single case because it's only one earthquake per study. And it does not really answer, are the anomalies found on these events or these earthquake events cannot be found on normal days as well. So this study adds a local multi-event framework. So this time we use multiple events, not just one, with event versus normal day analysis. Okay, so for TEC data collection, we use Ionolab TEC. And this figure here shows the exact location of the stations we used in this study and their exact locations in the Philippine map. So this is where you will see the contribution of each station code. We started with PMO, but since it failed to provide a complete data set that we needed, we looked for fallback stations, which are the PTAG and PTGG. There are still missing dates we tried to explore, but it failed to provide at least one date, so it's not retained on the final study. And you would notice that PMO vastly contributed our TEC dataset. So that's the reason why we presented this study as a PMO-centered GNSS framework. And on the other hand, these are the exact TEC data collected per year. You would notice that on the earlier years, there's only 52, less than 50% completion. And since we also want continuity, we only considered 2006 to 2025. When it comes to our earthquake data collection, we used the USGS COMCAT, or Comprehensive Catalog, and we use the following filters. Since it's risk reduction, so we are only concerned with the shallow events which can be more destructive. The other hand, magnitude 5 and above. And since for consistency, since USGS catalogs provides different types of magnitude types, we only selected those that are using moment magnitude to make sure that it will also avoid magnitude saturation issues. So as stated earlier, TEC is also highly influenced by space weather indices. And these are the exact major drivers, space weather drivers: the KP for global geomagnetic activity, DST for ring current density, and F10.7 for solar radiation level. So we want to make sure that the data that we will be using is not biased by space weather. That's the reason why we are using these indices with their corresponding quiet threshold to make sure that we will be filtering those that are not disturbed by this solar activities or geomagnetic activities. So next, this figure here shows our forecasting window. So for every day T, we wanted to know if there will be an earthquake that will be occurring in the next 24 to 72 hours. In order to know that, we will look for anomalies days before each day T. And then to know if there are fluctuations on the TEC values, we will be needing a reference, which is this baseline window as shown here. Okay, so to give us an idea how TEC anomaly detection works, let's use this example, March 13, 2022, magnitude 6.4 earthquake. So if the event happened April 13, then our recent day would be, or our main observation days would be March 7 to March 12. And since we want to make sure that our normal baseline would follow the expected solar cycle within 27 days, we also use a 27-day sliding window for our baseline, which is February 8 to March 6 on this study. Next, again, the space weather indices that we used a while ago was used to determine what are the reliable normal baselines that we will be using. We cannot use those that are disturbed by space weather. Therefore, those that are within the quiet threshold are retained as normal reference. So furthermore, in order to detect anomalies, we use this interquartile range method. So we only define our anomaly bounds, lower and upper bound, and whatever TEC values that are over this anomaly bounds are considered anomalous. So this plotted solid green here is the expected behavior if the TEC values are not disturbed. And the shade here that are not really obvious, but there's this shade lighter green here. These are the anomaly bounds that we are able to define. So the idea is that this alternating blue and red plot here are the actual TEC values that we collected. So blue if it's inside the threshold and red if it's outside, which are considered anomalies. So to give us a comparison on what the behavior of a baseline normal days and the recent mean observation days looks like, we can clearly see here that the recent days TEC values are elevated, suggesting anomaly. So again, it's not enough that we are only detecting anomalies. We want to make sure as well, how strong are these anomalies? Are they that far from the normal values? At the same time, we wanted to know as well, are they persistent? Are they repeated anomalies and not just isolated points? Third, we want to make sure again that it's distinct, that the patterns that we are seeing on the event days are not also shown on the normal days. And lastly, want to make sure that the signals that we will be obtaining are carrying predictive signals that are better than just guessed. So to give us an overview of how we detected the anomaly strength, we used two type of z-scores. So if the values are fairly distributed, then we can safely use the mean base shift to compare the average of the quiet baseline and the average of the recent TEC. However, if there are certain spikes or dips on the TEC values, then it's safe to use more stable z-score detection, which is the median-based z-score. And next, again, we are checking for persistence, anomaly count, anomaly proportion. We want to make sure that the anomalies are repeated, not just, for example, this one isolated, because we can only treat that as a usual spike or dip on the values. And then next, in order to know if these anomalies are distinct to events compared to normal days, we use these two metrics. So the ROCAUC, or the receiver operating characteristic area under the curve, and the other one is the precision recall area under the curve. So to put it simply, ROCAUC just tells us if the predictive scores or signals of event are higher than normal days. And second, we want to make sure as well that the prediction that we are making are accurate and are not false alarms. So since we use machine learning on our study, we use 3 candidate models for just logistics regression, which works by combining input features into one score, and then that score is converted to a probability 0 to 1. Then next, we also use the random forest model. So the idea of this is having many decision trees, and then the majority of the decision will be the final predicted output. And then lastly, the extreme gradient boosting, or the XG boost. So the idea of this is also tree-based, but every time it detects something is wrong, it will continuously build like an extra branch or tree until the whole system is corrected. So going back to our forecasting window, each output or predictive value, risk score 0 to 1 or low to high. Again, since we are aiming to providing alerts, we will be checking if these scores are over the cutoff score. And if that's the case, there will be an alert, otherwise no alert. And since we want to again make sure that the prediction is correct, we will be classifying them into this confusion matrix that we will be discussing later. So we use 3 stages on our model evaluation. First, we trained the models, and then on the validation or the testing or the tuning of the second stage, that is where we tested multiple cutoff selection rules. Multiple cutoffs. And the cutoff score that produced the highest recall, so recall is how many, the higher true positives that were captured within the false positive rate of 10%. And once we are able to select a specific cutoff score, that's the only time that we applied it to our evaluation. So this is what confusion matrix looks like. TP for successfully captured event, false positives for false alarms, false negatives for missed event, and then true negatives for correctly flagged anomalies.
Kailan yung false positive?
False positive po, nag-alert tayo pero wala talaga nangyaring event. Yes po. So these are the, again, metrics that we use. As you can see, the highest score is 0.8412. So again, the baseline is 0.5 chance level separation, and we can see that the values are way higher, meaning we have a clear separation between normal and anomalous dates or event days, I mean. The only reason why I mentioned that the signal is limited because when it comes to our PRAUC, the shorter the distance, I mean, from PMO, the lower the data points. Therefore, the lower the base rate as well. However, even if these values are way higher than the baselines, we can see that these values are way below 1 since we evaluated or we integrated both metrics from 0 to 1. That's the reason why we highlighted here limited. So the metric shows that the signal exists. Can we turn these signals into alerts? So first, with our true negative, it is expected that these are high values since, again, our data set is dominated by normal events. So these, again, are true negatives. These are the normal days that are correctly flagged with no anomaly. So second is our false negative. So false negatives are, we are not able to give an alert, but in reality, there was an earthquake that occurred. That's why it's a false negative. And again, since the purpose of this study is quantifying the predictive values of TEC anomalies, we are not aiming for 100% capture, but risk reduction. And third, our true positives. So these are the actual earthquakes that we are able to capture successfully. And again, if you would be comparing these values, I know that it's not high as we are expecting, but we should take into consideration that our data set, again, is dominated by normal days and that predicting an earthquake is extremely hard. And lastly, our false positives. Again, we gave an alert, but there's really there was no earthquake that occurred. I highlighted here this trade-off because every time we are aiming for a higher true positive, the false positives are also increasing. That we want to avoid as soon as possible, as much as possible, I mean. Because if there is a higher false positive, it means that every time the model gives an alert, which will induce panic, which we don't want to happen since, again, our design is risk reduction without panic. On the other hand, again, remember that we excluded some events on our original USGS catalog. We only use those moment magnitude family or magnitude type, and then magnitude 5 or above earthquakes. These are the example of those events that were flagged as false positive. So why was it flagged false positive even if there's clearly an earthquake that happened on that specific date? It's because, again, we remove those earthquakes that are lower than 5 magnitude of 5. Therefore, the model checks our catalog and it's not there. Therefore, the model assumes that there's really no earthquake that happened at this specific date. This is one of the limitations, or a good recommendation that can be done into future work. But again, since I'm aiming for a risk reduction model or framework, I still push through with more than 5 magnitudes, since these are the earthquakes that are more destructive compared to those that are 5 and below. So next, we also tested if the space weather filtering that we did are effective. The idea of ablation is we compare the same framework with and without space weather filtering. So when we remove space weather filtering, we are expecting that the values will degrade. However, it's the opposite that happened to random forest model. Recall or more events were successfully captured, and at the same time false positives were reduced, which is a good thing. So this tells us that there's a possibility that the space weather filtering that we did is too strict, since we are requiring 14 or more normal days that are quiet. That's the only time that we will use that exact event on our data set. So before we conclude, I do want to highlight this, why this study matters. First, we explored a 3-day forecasting horizon. So from seconds of reaction, we will be able to give communities exact or enough days, to prepare. Second, our event versus normal day classification accuracy is 92%. So we are able to successfully separate normal and event dates with this success rate. Third, what made this study possible is that everything that we needed, the TEC data, space weather indices, and the earthquake records are publicly accessible. So anyone who's interested in pursuing this topic can definitely do so. And lastly, we are aiming for this to be like a starting point in terms of Philippine TEC earthquake forecasting. So to conclude, we saw that TEC anomaly behavior was observable. TEC descriptors carried measurable signal. Again, alerting utility was present but constrained, the trade-off that I mentioned. The higher the true positives we want to capture, the higher the false positive. That again will induce panic. And I do want to mention that the findings remain cautious, since we found some limitations on the study, as I have mentioned a while ago, and there are still a lot to improve, such as um, adding more stations compared to just using one station or PMO-centered framework. So overall, this study demonstrates that the Philippine TEC anomaly descriptors are not merely visual observations. They can be quantified, tested, and shown to carry limited but meaningful forecasting information. While it's not yet sufficient for a real-time earthquake prediction, the framework provides a reliable foundation for future multi-station TEC forecasting research in the Philippines. So as a recommendation, again, we want to expand to more stations, larger and longer event dataset, spatial analysis, and then we also want to revisit our filtering strictness. So that ends my presentation for today. Thank you.
Okay, thank you very much, Jackie, for your presentation. Now we'd like to turn the floor over to your thesis panel, starting with the examiner.
Thank you, Jackie. This is a very interesting study. May I start, however, with the physics of your study, notwithstanding the three prevalent models, si Laik, si coupling, at saka ano yung isa? Electric coupling,
Yes.
and the other one? Positive hole theory. I just scanned through the merits of each of these at may konting katotohanan at pero mas maraming imagination, di ba? My question is, based on your 4 year-ish study of physics, is there a way wherein the stress between tectonic plates can produce an electromagnetic phenomenon enough to disrupt the distribution of the TEC based on the physics that you learned?
To be perfectly honest, that's the reason why I only used it as scientific motivation, because these are just proposed ideas. So I would say, based on my knowledge, or the things that I've learned for the past few years, as of the moment, it cannot be proven 100%. But again, we are using this as study motivation or scientific motivation.
So in your learned opinion, is it possible to generate an electromagnetic event based on stress, mechanical stress? In other words, when you compress something, is it possible to produce an electromagnetic effect? What have you learned in physics that tells you pwede or hindi pwede? Can you produce electricity from pressure?
Yes.
How? Or what type of materials do you need? Kasi, Jackie, this is not yet the earthquake event, right? These are
Yes.
days. In your modeling, it's T-6, right?
Yes.
These are days leading to an earthquake. Okay, imagine an earthquake about to happen. What's going on? Ano ang nangyayari bago mag-earthquake? Based on our current theoretical framework for earthquakes that are tectonic in nature.
Based on what I know, the tectonic stress builds up.
Yes, dahil nagbabanggaan
Yes.
o kaya naghihiwalay yung dalawang nag-uumpugang plates,
Yes.
di ba? Pag nagbabanggaan sila, there is enormous stress
Yes.
or pressure between the two. Actually, ito nape-pressure, ito nape-pressure.
Yes.
Based on that, is it possible to produce an electromagnetic anything, event, phenomenon, based on what you learned in your several physics courses?
Can you elaborate, sir, or give any example?
Can I what?
Like elaborate or give more specific example.
Yeah, ang tinatanong ko lang is, pag may nagbabangga ang dalawang bato, is it possible to create electric charges, electric field?
To be honest, I know that electric charges are possible, but I'm still quite contemplating if it's possible to create electromagnetic.
Have you heard of materials called piezoelectric?
No.
No. Sinong teacher mo sa solid state?
To be honest, sir, I've stopped studying for a couple of years. This is the only time that I went back to finish my thesis score. So I apologize if I'm not able to retain the information that I
That's
have
okay.
before.
That's okay. But this is the physical basis of your study.
Yes.
If events leading to an earthquake could affect the ionosphere, and the ionosphere could only be affected by electromagnetic phenomenon like solar radiation, geomagnetic events, di ba? Then therefore, there must be a correlation between nagbabangga ang tectonic plates. Kailangan i-correlate mo yan with an electromagnetic event. And it is possible because piezoelectric materials, pag kinompress mo yung mga yan, magpo-produce naman talaga yan ng electric field, ng electric charges. So there is physical basis to TEC anomalies. Hindi ko sinasabing totoo, but there is.
Yes.
There is a probability, very distinct probability na pwedeng mangyari yung sinasabi ng ng mga studies na to. Na pag may anomalies sa TEC count,
Yes.
pwedeng caused by tectonic plates. On the other hand, there are two types of tectonic earthquakes. Pwede sila magbanggaan,
Yes.
enormous stress. Pwede rin sila maghiwalay.
Yes.
So dahil magkaiba yung events, magkaiba rin ang effect dapat sa ionosphere.
Yes.
So that's one way of testing these theories kung, di ba?
Yes.
Okay. That's the physical basis of your study. Number two, my second question is, ano ang parang selection criteria mo doon sa threshold na magnitude 5? Kasi doon galing yung mga false positives mo.
Yes. Based.
Had you lowered it down to magnitude 3, liliit ang false positives mo.
Yes.
Because pakiload mo yung TP na slide through positives. Yeah. It is disturbing for me to notice that there are more FPs than TPs. If you are talking about the predictive virtue of anything, kailangan mas maraming true positive
Yes.
kaysa false positive. When I read your methodology, nakita ko kung saan galing. Doon sa MW5 mo.
Yes.
So my question is, bakit ka nag-select sa MW5? Bakit hindi mo binabaan or tinaasan? Anong selection criteria mo sa MW5?
Yes. Because to be honest po, since we want to be informed of possible destruction, usually magnitudes 5 and above are destructive.
Oh, so you considered the effect,
Yes. Yes.
not your methodology.
Yes.
But having known, nung nakita mo na to na tandami kong FP,
Yes.
bakit hindi ka nag-adjust?
Yes, sir. Because I want to push through the purpose of like alerting everyone. Because if it's
This would,
Mhm.
pag dineploy natin to, panic to.
Mm.
Panic. The panic arising from this thing will be worse
Yeah.
than the thing that we are trying to prevent.
Yes.
Mm.
Yes, sir. That's actually a good suggestion, sir. But to be honest, since it's already the final results, I thought that it's too late for me to adjust to a lower magnitude. But based on what I mentioned a while ago, these are the exact examples of
Yeah, ilang cases yung ganyan mo? Ilang cases yung below 5 na magnitude?
I think this is just for the year 2020, 50.
Isang taon pa lang yan, di ba?
Yes.
Ganyan na karami.
Yes.
Yan ang nagparami ng false positives
Yes.
mo, the below 5s. That's my second point. I think you justify mo maigi yung 5, and in the face of the data that you gathered, you revisit it, you may want to readjust it,
Yes.
and then justify it further. Bakit mo nire-readjust? The goal is to make FPs always greater than, always less than
Yes.
TPs.
Yes, sir.
If we are. And then on a minor note naman, in your discussion, you always downplayed that you are talking about a predictive device, right? Yet in the title, ina-upplay mo yung predictive. So ano ba talaga? So they have to be consistent. Pag ayaw mong i-focus yung predictive, palitan mo yung title. Kasi the title implies na predictive siya. But your study has proven that there is correlation. So it's correlative, not predictive. Wala pa tayo doon sa predictive power niya eh. Kasi yung methodology mo kailangan pang ayusin talaga. And one thing nga is the false positive problem. Pag naayos natin yun, saka mo siguro pwedeng gamitin yung word na
Yes.
predictive and no panic.
Yes. Yes.
And there are some minor grammatical errors and every time mag-quote ka ng author, halimbawa, maglambayan ba yun? And
Yes. Maglambayan.
yeah, maglagay ka agad ng reference number kung saang article mo yun kinote.
Yes.
Kahit meron na sa reference mo, dito sa body, ilagay mo ulit.
Yes.
Para masundan ng author. Parang ako, saang paper to kinote? Hindi ko masundan kasi walang number kung saan mo kinote yun. Sa end ng, wala dun. Pero may number, mga 3 sentences later. Baka yun. Oh. So, doon mismo sa sentence na ginamit mo yung pangalan,
Yes.
doon kayo maglagay ng number kaagad.
Yes.
Para specific talaga yung citation.
Okay, hello, Ms. Rivera. So, congrats for your presentation. So, I'd like to clarify the data that you get from the stations kasi majority is from one station, no? So, are there duplicates? Kasi fallback station yung dalawa. Are there duplicates in the data? Or
Yeah.
pwedeng stand-alone yung first station mo without the fallback stations?
Yes, sir. The data points between these stations are unique from each other. We used a hierarchy, like we tried to collect data first from PIMO because that's our main station. And then since it failed to like provide 100% completeness, that's the only time that we use this to fallback station, and we gathered this 250 and 7 TEC estimates.
So you only select the fallback pag kulang yung
Yes.
nandun sa
Yes.
major station mo.
Yeah.
Okay, so in terms of the data set, parehas ba yung distribution nung major tsaka dun sa fallback? Kasi observation mo to, di ba?
Yes.
So yung data, pareho ba yung distribution nila?
Yes.
Yung rate, yung rate ng acquisition nung data set, is it the same?
I'm sorry.
Kasi hourly ito, tama ba?
Yes.
Up to hourly na data. So kung wala yung isang, let's say, week or isang hour, doon mo siya ipapasok doon sa hourly din nung major station, ganun ba?
Yes, sir.
So meaning para sa yung resolution.
Yes, sir. Yung parang yung sa PIMO po, yung kulang niya parang isang buong day.
Okay. So possible yung ginamit mo na temporal temporal component. So dinivide mo siya into 3.
Yes.
Then at the onset of the earthquake, you have 2 small temporal beams. Ano ba yan? 5 and 3, 3 to 5. Yon. So what is the significance of your 3-day window? Is it based on the previous research about anomalies or nag-average ka?
Yes, sir. When it comes to the 3-day window, partially, yes, it's based on previous studies. But at the same time, because if we will only use let's say 1 day instead of 3 days, it will be harder to like predict an earthquake if we only have 1 day lead time. That's why we like expanded it to a 3-day window, the higher chance that it will be able to capture an event.
So T plus 3 also.
It's not the T minus.
Yes.
So we're not talking about predicting near tapos na yung earthquake.
Yes.
So ano to? Hindi na siya onset. Yung T+3.
Tapos 3 days later na yun.
So does this T value related dun sa pagkuha mo ng delta mean? Kasi dun sa delta mean, no, you have the what? Yung recent
Mhm.
minus the baseline.
Yes.
Ano yung T doon na ginamit mo? That's equation, I think, sa methods mo. Equation 3.5. Delta mean is the mean of recent minus the baseline.
Sorry.
Is it the same time scale ito? Yung T na to? Equation 3.5. I'm assuming na yung mean ng recent at mean ng baseline, moving average ito.
Yes po.
Tama ba? So
Yes.
cumulative siya. Yung
Yes.
values. Correct?
Yes po.
Sige. So what is the basis of your ang tawag doon? Yung delay time dun sa actual na time scale ng TEC. I mean the variation of TEC. Because you can have variations in TEC to as scales ng hours or even several days. Diba?
Yes.
So each time that there is a specific event pero hindi mo siya ma-pinpoint, yun yung window mo.
Yes.
So how sure are you na yung lead time mo na 3 days is the best one to pick?
To be honest, I'm not able to test other forecasting windows. I just stick to the 3-day time frame.
Pero yung ibang studies, ganun din yung ginamit.
Yes.
So is there an assumption na dun sa window na yon you get large changes dun sa TEC?
Yes.
In terms of the whole data, let's say 2006 to 2025. Tama ba?
Sorry.
Yung anomalies mo, yung changes mo dun sa T or sa TEC is measured across all data from 2006 up to 2025. Lahat yun yung kinover mo to get your assumed na T, which is 3 days.
Here po. So we use 3 stages. So not all the years from 2026 to 2025 are evaluated on the values that we have on the confusion matrix. So part of those years are used for training the models, for validation to choose the cutoff score, and then the rest are the one that were evaluated.
So po pwedeng mas malaki yung T mo, ano? Mag-adjust ka.
Yes.
So now, ito ay sa temporal scale lang.
Yes.
But usually, you use TEC to what? Para dun sa line of sight nung determination ng epicenter per receiver. What is the time scale for the redistribution? Dun naman sa, let's say, an ionosphere. Kasi ito ay parang global na siya na ano na space or volume. Are we still talking about the same time, let's say days? Hindi ba siya nagbabago for a larger time scale? Let's say months, similar to atmospheric disturbance. Kasi kung may redistribution ka, merong delay spatially. So you've studied temporal scale. So can we account for the redistribution spatially with the same time scale na base din?
I think we could, but since I'm not able to like calculate the exact time frame, I will not be able to say the specific time frame that the redistribution will occur. But since it's 5-day anomaly detection, so
Nung nag-identify ka ng threshold, ano yung pag-classify mo nung quiet at saka doon sa disturb? Ano sinasabi ng indices mo? Let's say nag-pick ako ng isang value. Ano sinasabi niya? If it is lower, ano yung kino-consider ko doon na effects na hindi ko consider if it is above and vice versa. Kasi numbers lang to, di ba? Pero ano yung physical na attribution ko doon sa pag-identify ng threshold? Whether I filter other geomagnetic phenomena. Yeah. Parang ganun.
Solar
Storms.
pag KP is less,
Mm.
pag sa F10 and less.
yes po. But from what I know po, when it comes to the resolution of both KP and DST, these are early, changes early. However, this solar radiation level is based on the data that I have collected, it's daily.
Okay.
Yes.
So, okay. So, yung final na comment ko ay dun sa recommendation about spatial analysis. Ilan yung possible na stations na or available na stations dito sa Philippines?
There are actually stations that were installed. Let's say PIMO was installed 1998. At the same time, there are other within five stations. The rest are actually
Saan yung location yan? Saan yung location?
the rest are installed around 2008 to 2014.
So, does it mean we can reduce the epicenter ay yung i-consider mo na region from the epicenter? 1, 2, 3.
Yes.
Ito lang siya.
Yes po. So ito lang yung ginamit ko pero dun sa website ng stations, yung buong Pilipinas po merong kanya-kanyang station. Kaso yung pinili ko po ay yung pinakamalapit sa PIMO.
Yun ba sa amin, sinasabi niya. Kasi kung redistribution lang yun, pag nag-pick sa ibang lugar, mag-delete naman sa ibang lugar.
Ilang stations yun natin?
Oh.
Ilang stations yun natin?
Yung ginamit ko po ay yung available. Hindi ko po nabilang pero available po siya sa pwede po ma-search.
Di ba?
Sige po.
So is there an open data na similar siya or lower resolution pag sa, let's say, NASA na database? Or sa atin lang? Meron.
Sa atin lang po na stations lang.
So hindi open yung data dito. Yung database dito sa Philippines na ganitong resolution, can we also access that sa NASA na data set?
Not able to check po because I collected this directly from Ionosphere. So dun sa Ionosphere po na website, papalitan mo lang yung station tapos makukuha.
Ay, so nandun na rin yung
Yes.
stations. Okay, sige. So no problem. Sige, no further comments.
Thank you very much for questions from the panel. Now we there are a couple of questions from the audience, particularly from one of our faculty members in DPS, Professor Dib Javier. So first question is, can the sensors delineate between tectonic and volcanic earthquake?
Can you repeat that?
Can the sensors delineate between tectonic and volcanic earthquake?
Based on the framework that we have, it did not account to difference in earthquake generators.
Okay. Pero yung sensors particularly, may idea ka ba kung nadidistinguish niya yung tectonic or ano?
Based on related studies po, as of the moment, wala. Wala.
Yes.
Yes.
Okay. So yung second question is, how much in percent of the data was used for training and validation?
So majority of the data was used to train the model. Yun po yung nilagay ko sa appendices, pero I'm not able to put it on the slides. But
So
I'm not able to count it, but majority was used in training the model. And then I think there's a similar proportion when it comes to the number of years used on the tuning and the evaluation period.
pero sa training mo, hindi mo ba siniset yung ano? Yung percent?
No po, yung year ang nilalagay ko mas. Parang 2006 to
okay,
2015, parang.
so ganun mo siya sinet?
Yes.
Okay, not necessarily. Okay. I don't see any other questions from the audience. Maybe from the audience present. Are there any questions? You have a question?
If the TEC in the ionosphere has cyclic changes throughout the year, I was wondering if that baseline would be accurate, like that part of the month.
Annual average.
Oh,
Annual average.
yeah.
Sorry, question specifically?
Oh, I was wondering if it would be accurate to have a baseline be one section of the year. If if the TEC is cyclic, it might not represent the following weeks the same.
Nakuha mo yung question?
Yes. To be honest, that's actually a good point. If we will just get the baseline or the normal behavior like as a whole in a year. But again, this idea is from the previous studies that were proven. But again, that's a good point that we may consider in future work.
Okay. Any other questions? Okay, so I think that's it. So maybe just to summarize, yung work na ginawa ni Jackie is about earthquake prediction, but mayroong suggestion actually of course yung ating examiner si Professor Garcia and also si Professor Javier, maybe to use the phrase potentially predictive kasi mababa yung success rate. Or correlative,
Yes.
as suggested by your examiner. Yeah. So with that, I would like, you have one. Sige.
The study that I have is not yet a real-time prediction, but I get your point. I will not be able to tell it yet as of the moment, but as much as possible, I would like the same alert type. If you have experience receiving like a notice from NBRRMC, like right, even if you don't have Wi-Fi or you don't have the data on, it still alerts your phone. So that's what we want, but as of the moment, it's not on the scope of my study.
Okay, great. Thank you very much for your questions. These are coming from our freshman BS Physics students. At this point, we'd like to thank Jackie for her presentation and congratulations for this work.